So in the last section, f is equals to minus kx. This was our equation 1. So now kinetic energy T of the particle is given by T is equals to 1 by 2 mv square. So which is equals to T is equals to 1 by 2 and x dot square. So this x dot square, where x dot or the v is equals to x double s dx by dt. This v is equals to x double s dx by dt. Since restoring force F is a conservative force, so it can be represented as F is equals to minus of dv by dx, which is equals to dv, so which is equals to minus of f dx. This is our equation 3. So using equation 1, so equation 1 we have f equals to minus of kx. So this equation using equation 3, in equation 3 we have minus of f dx. So simply substituting the equation 1 and equation 3 we get, so minus already we have minus of bracket inside minus kx. Minus cancel, so we get dv will be equals to kx dx. Now in the next session we will be integrating in both sides.
Start.
So in the previous section, integrating both sides, integration of dp is equals to, so k is our constant, it remains as it is. So integration of x dx is equals to v kx square by 2 plus of c. So c is our constant. So using boundary condition in this equation 4, we get that at x equals to 0 and v is equals to 0 in this equation, using we get, that means when x is equals to 0 and v is equals to 0, this whole term becomes 0. So finally we get only c. Therefore c will be equals to 0. So v we get v is equals to kx square by 2 plus of 0, which is your equation 5. So in previous section we had two equations, that is t is equals to 1 by 2 and x dot square, which are our equation 1, and v is equal to 1 by 2 kx square, which is our equation 5. Right now we got. So in Lagrangian equation we use L is equals to t minus of v. So in this equation, so we have got the two values of t and v. Now using these values we get L is equals to 1 by 2 and x dot square minus of 1 by 2 kx square, which is our equation 6. So now we have got this equation. Now partially integrating this equation with respect to x dot as well as x, we will discuss in next section.
Start.
So in the previous section, 1 by 2 and x dot square minus 1 by 2 kx square, this was our equation. So partially differentiating this equation with respect to x dot and x, we get that. So del L by del x dot equals to 1 by 2 m to x dot. So differentiating with x dot, we get second term, our this term totally becomes 0. So our equation only remains this 1 by 2 and m to x dot. So this 2 gets cancelled. So del L by del x dot we get mx dot, which is our equation 7. So similarly same equation 6, partially differentiating with respect to x, now we get, so differentiating with respect to x, this term becomes our 0. Therefore 0 minus 1 by 2 kx, so k is our constant, it remains as it is. So x 2x, so this 2 gets cancelled again. So therefore del L by del x equals to minus of kx, which is our equation 8. So now we got the two equations, that is 1 del L by del x dot equals to m x dot, equation 7, and del L by del x. This is del x dot, del x equals to m minus of kx, minus of sorry, this one is minus of kx. This is minus of kx, and here is minus of kx is the equation 8. So we got the two values. Now in the previous section, using Lagrange equation of motion, we have to substitute these two values. In the next section, we will use Lagrange equation.
Start.
So in the previous section, we have got the two equations, that is chord A by chord x dot equals to mx dot, equation 7, and chord A by chord x, which is our equation, equals to minus of kx, equation 8. So these are the two values. Now in using in Lagrange equation of motion is given by d by dt, where chord A by chord x dot minus chord A by chord x equals to 0. So this is our equation 9. So this is the Lagrange equation where we will be using these two values. So using equation 7 and equation 8 in this equation 9, we get, so d by dt mx dot. So chord A by chord x we have got, chord A by chord x dot we have got mx dot. So d by dt mx dot minus, so dl chord L by chord x we have got minus of kx. So minus bracket of minus kx equals to 0. So this minus minus gets cancelled. So then we get x double the dash t omega square x equals to 0. So this is our final equation for the Lagrange equation for the linear harmonic oscillator, where this x double dash means x equals to d square x upon dt. This is our equation. So now using here, we have again here omega. So omega means where omega square is equals to, we have k by m, or we have, so the final equation we have got, that is x double dash t omega square of x equals to 0. This was our final equation. So here x dot means d square, x dot means d square of x, d square of x by d t square. Similarly here omega square. So omega square means frequency. So omega square equals to, so the final equation we have got was x double dash t omega square x equals to 0. So where x double dash means d square x upon dt square. Similarly omega means frequency, so omega square equals to k by omega square is equals to k by m, which is equals to omega square means 1 by 2, so that is root of k by m. And now v is equals to 1 by 2 pi root of k by m. Similarly t, so t is equals to 1 upon v, that is 1 upon v. So this will become 2 pi root of m by k. Simply the reciprocal of v. Reciprocal of v we get 2 pi by root upon m by k. So the final equation this is the final equation we got. So this solution of equation can be represented as x times of t, which is equals to a sine of omega t plus of phi. So this, with using this equation, we can use linear harmonic oscillator in classical mechanics. So A sine, omega and phi, these two values will vary. So finally I have completed my topic. So I could not complete the quantum concept of linear harmonic concept as it was too vast. So hope you all will understand it. Thank you.